In this video, we're going to take an introduction to logarithms. We're going to define what the logarithm is. We're going to look at how do you switch between an exponential function and a logarithm. And we're going to look at a few special bases and eventually get to the change of base formula. So this statement right here, we have a equals b to the n is equivalent to the log base b of a equals n. This is a statement that we use to define a logarithm. Now, a logarithm is not something that we can define with an equation. There's not a function I can write down that you plug things into to get an equation to find a logarithm. Logarithms are things we generally look up in tables, or we use computers or calculators, which generally just look it up in a table. So the way we define the logarithm is we connect it, we show how the relationship connects between the logarithm and the exponential function. So over here, a equals b to the n, this is our exponential function. And I'm going to say this is an exponential form. That's what we're used to working with. Now, I didn't use x and y because it starts getting confusing as we go back and forth between the two. Where does x go? Where do y go? Because we generally refer to x as independent as the input and y as the output. And they're inverse functions, so they change positions. So I use a and n. In this case, n is my input, my independent variable. A is my output, my dependent variable. And b is the base. Now, one thing to keep in mind as we are doing these exponential functions and working with this, the base is always going to be greater than 0. We're not going to work with a negative base. That's not something we work with when we're looking at exponential functions, especially when we go into the inverses and we start going with the logarithms. It needs to be a positive base. The other thing is we can't have our base equal to 1. Because if I say a equals 1 to a power, that's just a equals 1, and that's of no interest. But as a result, since my b is always going to be non-zero, if I take a positive number to a power, no matter what the power is, I'm always going to get a positive number out of that. So my a has to be a positive number, my b has to be a positive number, but my n can be any real number. So we can use anything we want as an inverse. We can't, or as an exponent. So, in other words, domain is all real numbers, but the range is going to be y is always greater than 0. Now, when we go to the inverse, we're going to call this the logarithmic form. Let's get this a little better here. Oh, how about erase? That might be a little better. Draw. And we're using the same letters, A, B, and N, because we are representing the same relationship. But in this case, A is the input. And B, sorry, not B, N is the output. We're talking about an inverse function. So we switched input and output to get our inverse, and we switch our x and y. B is still the base. And the B is the same whether we talk about the exponential form or we talk about the logarithmic form. They have to have the same value of B. They have to have the same base. So, again, your B is going to be greater than 0, but your B cannot equal 1. It's related to that exponential function. So those are defined in the same way. Your A value, it's the same values. So the A still has to be bigger than 0. So in this case, my domain is the A this time, and that's the one that's bigger than 0. So my domain is going to be x is bigger than 0. My range, dealing with the y's, the outputs, well, this time the output is r, the output n is any real number, so the range of the logarithm is any real number. The way to define what is a logarithm is to refer it back to the exponential function that it comes from, that it's the inverse of. But we got to keep track of this base, because for every different base, there's a different logarithm function. So that base is very important. One of the main ways we use this relationship is to switch back and forth between different forms. So if I had the equation 12 to the x power equals 400, this is an exponential form. I could rewrite this over into logarithmic form, and I would say my base is 12, so this is going to be a log base 12. My input is x, so that's going to now be my output. The log base 12, that's going to equal the number x. And then my output from the exponential is going to be the input from the log. So that's at 400. The log base 12 of 400 equals x. I still don't know how to evaluate these things, but if I can evaluate this logarithm, now I can find out what x is. I've changed this from exponential form to logarithmic form. Now I can go the other way around. Let's say I have a problem. The log base 5 of x equals 7. I can come along and let's say again, my base is 5, so that means I have 5 to a power. My input is x, so that means my output's going to be x. My output 7 is going to be my input. So now I have 5 to the 7 equals x. That's a problem I can plug into the calculator and do. So this is that advantage. If I am looking at a problem and I have an x in the exponent, I don't know what to do with it. If I switch it over to logarithmic form, it's no longer in the exponent and it's an easy problem. If I have a problem where my variable, my x, is inside a logarithm, I don't know what to do with it. I switch it over to exponential form, and now it's out, it's the answer, and I have a way to deal with that. So one of the main reasons we use this is to switch back and forth to whichever form is more useful to use. The other thing to remember is, since they are inverse functions, don't forget what it means to be an inverse function. That means if I would take b raised to the log base b of x, if I take a logarithm and then I plug it into the exponential, I'm doing the composition of two inverses, I get back, I plug in x, I get out x. Or likewise, if I say the log base b of b to some power, I'm first doing the exponential, and then I'm plugging that answer into the logarithm. I'm doing a composition of inverse functions. My output is going to be my input. So now that we know how to put this function into logarithmic form, how do we get the values of that? So it all depends on what the base is, because every different base has a different log. So we're going to start with the common log. The common log is going to be base 10. We're in a base 10 number system. Every time you multiply or divide by 10, you move one place value. So this is the one we use the most. So when we're taking the log base 10, the common log, we don't write anything. We just write log. This really means the log base 10. We just don't write that. The same way that with a square root, we don't put the little 2 in there to show that it's a square root. It's the one we always use. The nice thing about this is your calculator has a button that says log. That is the common log. So if I were to want the common log of 100, if I plug that into your calculator, you hit log 100, you will get 2, and that's because 10 to the second power equals 100. When we do the logarithm, we just get the exponent. Common logs, as I say, it's common, the one we use the most, so it's pretty nice. Another log that gets used quite a bit, especially in the sciences, but you'll also use it if you go farther in math and you start working in with the calculus, it shows up quite a lot as well. This is what we call the natural log. And the natural log is base e, And E is something we might talk about another time. E is called Euler's number. And it is approximately 2.71828. And it is like pi. It's irrational. It goes on and on forever. But if you look at natural growth, you look at things that grow exponentially out of nature, they can all be written as base E. So it's one that we use a lot when we're talking about natural growth, which is why we call it the natural log. So if we're talking about the log base E, we use ln for natural log. I know it's backwards. And again, your calculator has an ln button on it, because it is, again, one of these logs that if you do a lot of math and science, you use the natural log quite a bit. So if I want the natural log of 100, I'll plug that into my calculator, and I will get 4.605 approximately. And that is because if I take e to the 4.605, I will get about 100. So what do you do if you don't have base 10 or base e and you want to find a log? We can't have a key for every different log on the calculator, so we get a formula. And this is called the change of base formula. Change of base formula starts looking a little crazy. This says the log base b of x equals the log base c of x divided by the log base c of b. It's called change of base because we are going here from base b over to base c, with the idea is if I can't work with base b, I put everything in base c, I can work with that. Generally speaking, for c, we're either going to use 10 or e, because that's what our calculator would do. So for example, if I wanted the log base 5 of 100, my calculator doesn't do base 5, so let's make it base 10. That's going to be the log base 10, or the common log, of 100 of the input, divided by the log base 10 again of the base that I have, my old base of 5. And I will get about 2.86. Which means that 5 raised to the 2.86 is going to be about 100. Sounds good? 2 squared is 25. 2 cubed is 125. So it's going to be between 2 and 3, a little closer to 3. Now, we wouldn't have to do base 10. If I wanted to go to a different base, I could say the log base 5 of 100, I could go base e. So I could do the natural log of 100 over the natural log of 5. I'm going to get the same number. I generally use those two bases because those are on my calculator. They're easy. With this, we can do some work and we can solve some problems.